All right, guys, section 5.1. We are going to get an introduction into the problems of area and distance. So essentially, calculus itself. This was developed to answer 4 different problems, and it was developed in individual phases, so independently and separately. Number 1, it was developed to answer the question of the tangent line, like, how do we find the slope of it? We've discussed that. Optimization, how can you minimize or maximize something? We've discussed that. Problem of motion, velocity, acceleration, direction, how do they relate? We've discussed that. So we are now to the final phase of area. How do you find area of less traditional shapes? Okay, so like in middle school, you learn how to find area of rectangles, triangles, circles, etc. How do I find an area of something like this, this green space over here? So I'm going to start with this diagram on the left, and I'm going to ask you, how would you find the area of something like that? So how would you find the area? Well, the area would be, computed like a rectangle, because this really is just a rectangle, right? So we would do length times width. And then if I look closer at this particular rectangle, it looks like the width of that is 4, right? And we could refer to that width as the C value. If this was the equation y equals C, we could refer to the width as the C value. What about the length? Well, the length we're going to call, I could say it's about 4 units, but we're going to make it more of a formula-based representation. And we're going to say that the first point here is A, and the second point here is B. So I could determine the width by doing, length by doing the B value minus the A value. Okay, that's a little jumbled. Let me try to fix that. So the B minus the A value times the height, which is the C value, is how you're going to compute the area of this particular rectangle. So then what do you do for something like this? Well, what you're going to do is you're going to kind of do the same thing. You're going to make rectangles, okay? Because there's no area formula for a curved figure. We only have area formulas for things that are rigid shapes like squares, triangles, and so forth. Nothing for something like this. But what we could do is we could turn it into a series of rectangles, like so. So I could make it into sections, you know what I mean? I could make sections out of it and then draw rectangles for each section and find the area of all the rectangles and add them up. Okay, so if I were to do that, I would have an area that is pretty darn close to this one over here, but with the rectangles and the way they're drawn here, this area would be a little bit bigger than this one, right? Because the rectangles go over top of the space that we're trying to focus on. So how do we do this mathematically? Well, we're going to divide it into sections. So you will see that each of these rectangles are equal in their width. They each have a width of 1/4. Okay. So then the question becomes, if we know the width, how do we find the height, right? We know the base. How do we find the height? Well, the height of each rectangle is actually determined by where it hits the curve. Okay. So this rectangle has a height of 1 because that's what the y value is there. This rectangle, I don't know exactly the y value at this point, but if I were to find that y value, that would tell me where the rectangle hits on the curve and then would give me also the height for that curve. So how do we find the height of each rectangle? Well, if you knew where it hit the curve, you would have that number. So all you have to do is you're going to plug the x value, so in this case 3/4, into the equation for the curve, which is y equals x squared. Y equals x squared. Okay, that would give you the y value at that point, which is also the same as the height of the rectangle. All right, how do you find the area of each rectangle? Well, you would do area equals base times height. The base of each rectangle is 1/4, okay? And then the height is like the y value. So you're going to do 1/4 for the the width, I guess, or the base of the rectangle, and then multiply by the y value, and that's like the height of the rectangle. How do you find the total area of all the rectangles? You just add them all up. And that is essentially the process, guys. You're going to find the height of each rectangle. You're then going to find the area of each rectangle, and then you're going to add them all up to get a total area. And this technique is an estimation, okay? This is an estimation of an area for a non-traditional shape. All right, so here's a computation that's been completed just to show you what this may look like. So let me break it down for you. Right here, this is your width of the first rectangle. This is the width of the second rectangle, right? And so forth. These are all the width values or base values, if you will. And then this number here, if I were to plug the x value in and square it, and I'm squaring it, by the way, because the equation of this curve is x squared. So if I square it, that gives me the y value, which is right here, and that's equal to the height, okay? That's equal to the height of the square or rectangle. So then adding all of these values together gives you your total area approximation. So it's 0.46875. Now the statement down here says that the area is less than 0.46875 because remember, this is an estimation to try to find the area of this shaded space, and the rectangles, the way they're drawn, go over top of that. So I know that this answer is larger than the area that we are actually trying to find. Okay? What you could also do is you could draw your rectangles a different way. So what you could do is go to a point on the curve and make that like the corner of a rectangle, but then draw it to the right. So this is called a left Riemann sum. Riemann sum just means bunch of rectangles. It's a left approximation because the corner of the rectangle is on the left side of the left side of the rectangle is on the curve here. So the computation's a little bit different because the first rectangle is not there. It has a height of 0. The second rectangle, the height is determined by this x value. That's how tall it is. So we plug 1/4 in to find that value. Third rectangle is at 1/2 and so forth. So this time we get an area measurement of 0.21875. Now, according to the area we are trying to find, this is a little bit less than that value because it's not as much space. So what I've got here is I've got two approximations. One is a little less than what we're trying to find, and one is a little bigger. So I just have narrowed down that my area has to be between these two numbers. Okay, again, real quick with the left and right differences. So we are going to, from now on, refer to these as left sum approximations or right sum approximations. We also call them Riemann sums. It just means breaking something into pieces to estimate the area. So a left Riemann sum will be designated with a capital L, and then the 4 down here means how many rectangles or sections are used in that approximation. And then right Riemann sums will be a capital R, and then down here again, the 4 means it's divided into 4 sections. For this particular curve, the left Riemann sum is less than the actual area, and the right Riemann sum is more than the actual area. And that depends on the curve, actually. It won't always be that way. Okay, so how could we get a better approximation? Because this, this answer that we came up with here is not real great. It's a pretty wide range of values as far as like what's the actual answer. So how do we get better at approximating? To get better, what you do is you use smaller rectangles. You use more rectangles. So if I were to use 8 rectangles instead of 4, my approximation window is a little bit smaller, a little bit more precise. And then right here, if I were to increase the number of rectangles, that's what this means, by the way, number of rectangles. If I increase the number of rectangles, I get an even better approximation because now it's really hard to differentiate between the left approximation and the right approximation. So if I had 1,000 rectangles drawn, I get a pretty clear idea of what the actual area would be because these two numbers are very, very, very close together. But is it practical to draw 1,000 rectangles? Absolutely not. We're not going to be doing that, so don't sweat it, okay? Today, for now, what we're going to do is just kind of work on doing the basic estimation, you know, a small number of rectangles. And then in the next lesson, we'll discuss how to get a better approximation. Okay, so one quick thing. How do you divide an area into equal subintervals? So remember, when you draw these rectangles, they all need to have an equal width to get a good approximation. So how do you divide your area into an equal width? Well, don't overthink it. All you're going to do is you're going to take your B value, which is like the end of the interval you're observing or analyzing, and your A value, which is the beginning of the interval that you're kind of looking at investigating, and you are going to subtract those values and divide by the number of rectangles. Okay, and that is going to equal the width of each rectangle. For example, if this one was 2 and started all the way back here at 0, and I wanted 4 rectangles, let's say, then the width of each rectangle would be 1/2 of a unit. Okay, again, like I said, the general process of approximating the area under a curve by breaking it up into rectangles is called finding a Riemann sum. So that's what we're going to be working on. Okay, there's a bunch of different ways to do this. So I think what's going to be best, I'm going to skip this example. What's going to be best is if I'm going to create another video for you where I go through some of the Delta Math homework questions to show you exactly what you're going to need to do. Okay, so this one right here, just skip this for now. And let's go to the other Delta Math homework video for more information.